Authored by veteran chemistry teacher Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up, and don't forget to subscribe. We will see you in the next video, and thank you for watching.
Today our lesson deals with pH and pOH calculations in aqueous solutions. The concepts described will be the autoionization of water, ionic product of water, calculations of H and OH ion concentrations in acids and bases, pH calculations, pH changes. First of all, we're looking at autoionization of water. The point that is made here is this, that even though water is a molecular compound, the use of very sensitive conductivity instruments shows that it does conduct electricity very slightly. Scientists attribute this to the autoionization of water that produces tiny amounts of H and OH ions. So the Foley equation here is showing you the autoionization of water. Look how water autoionizes to give you hydrogen ions and OH ions. At 25 degrees Celsius, the concentration of hydrogen and OH ions are found to be these values. Notice how the concentration of hydrogen ions is equal to the concentration of OH ions. And because of that, water remains neutral, because every time a molecule of water ionizes, it gives an equal amount of H plus and OH negative. So even though water is autoionizing and is producing H plus ions and OH ions, it is still neutral at 25 degrees Celsius. Any substance added to water that changes this equality in the concentration of hydrogen and OH ions in water will produce an aqueous solution that is either acidic or basic. See right now, at 25 degrees Celsius, we have an equal concentration of hydrogen ions and OH ions. Anything that upsets this equilibrium here, where you're causing the OH to become more than H, will make it become basic solution, or something that causes the H ion concentration to get higher than OH ions concentration will cause it to become acidic. One point I want to note here is this. Remember we said that hydrogen ions do not exist by themselves there, but they cozy up in water molecules form hydronium ions. So for the purpose of this text, what we'll do, we shall assume that the hydronium ion concentration is the same as H plus ion concentration, right? So we won't be referring to hydronium ion concentration now. We were talking about the H plus ion concentration when we were doing all these calculations. Ionic product of water, Kw. You see, because this thing is a constant, at 25 degrees Celsius, these values remain constant. So what you try to do is to have what is called an ionic product for these ions here, okay? And it's called Kw, the ionic product of water, which is formed by multiplying the concentration of hydrogen and OH ions at 25 degrees Celsius. So it becomes 1 times 10 to the negative 14. Point to note is that at 25 degrees Celsius, regardless if your solution is neutral, acidic, or basic, when you multiply the concentration of hydrogen ions and the concentration of OH ions, it will always become 1 times 10 to the negative 14. Based on this understanding, the following can be inferred for any aqueous solution. If this one increases, then this one must increase proportionally such that the ionic product remains this. If OH increases, then the H must decrease proportionately or proportionally such that the ionic product stays the same thing at 25 degrees Celsius. So based on that, we'll have these equations now. All right, can derive these equations. We know that kW is equal to this times that. So we can manipulate this equation here to find for any one knowing the other two. And someone will give you OH concentration of the solution. You can now find H by putting kW and dividing that by OH concentration. If you know what the H plus is, and of course we always know what kW is, you can know what OH ion concentration is. So hold these three equations together as we'll be using these to find out the concentration of hydrogen ions in a solution given OH, and we'll be required to find the OH ion concentration in a solution given H, since we know what kW is. Let's see what happens when you add an acid to water. Let's see how the concentration of H and OH changes, okay? All right. In water, the concentration of these two things are the same. H as well as OH is the same. So we show you by this graph here, can see that concentration is the same as that, okay? We're showing the OH there and H. Before you add an acid, this is what we have in here. Equal concentration. And this is the product, all right? Let's see what happens after you add an acid. When you add an acid, what are you adding? You are adding H plus ions to it. So every time you add an H plus ion, it will seek out an OH ion to neutralize it. So let's look at these figures here. Before you add H plus from the acid, you can see inside here, you're having an equal concentration of H and OH ion because it's neutral. You haven't done anything to it yet. When you add hydrogen ion now, what each hydrogen ion will do is to seek out an OH and neutralize it. So 4H or H ion will neutralize 4 OH ion. That's what we're doing here. And it gives you 4 molecules of water that's neutral. So I'm showing you how that is going to happen here. Okay, and then that is the result here. So look what happens. Because you're removing OH from the solution and locking them up as water molecules, the concentration of hydrogen ion gets higher than the concentration of OH ion. If you look at this figure here now, you can see that the hydrogen ion concentration went up and the OH ion concentration is lowered. But the point is this: you have a higher H than OH, but when you multiply the new hydrogen ion concentration with the new OH ion concentration, it results in the same value here, which is the kW for water. This is the point. Never mind you're adding hydrogen ion to the water, that is increasing the concentration of hydrogen ions and lowering the concentration of OH ions, right? In the end, whatever values you end up with for H plus ion and the OH ion, when you multiply these, you will still get 1 times 10 to the negative 14 addition of a base. When you add a base, the opposite is going to happen, all right? Before you do that, you have water here, neutral. The concentration of these two guys are the same. Of course, that's the value for kW. See what happens now. When you add a base, you're actually adding OH ions to it, right? Each OH ion that you add takes out an H ion. See? The OH here is reacting with hydrogen to give you water. And I'm showing you that here, and that is the result there. The effect is that the solution will have a higher concentration of OH ions than hydrogen ions. All right? So now you have a different skewing there. This one went up a little bit. And that one went down proportionately. But when you multiply these values, you still get that value there, okay? So let's summarize all you're having there now. In an acidic solution, the concentration of the hydrogen ion is greater than the concentration of the OH ion. In a basic solution, the concentration of hydroxyl ion is greater than that of hydrogen ion, and in a neutral solution, the concentration of H plus ion is equal to OH ion. Okay? The ionic product of water, Kw, which is the product of H and OH, is always this value. Based on that, if you know OH, you can calculate H by putting this value here over the OH. If you know H, you can calculate OH by putting Kw and divide it by the concentration of H plus there. So this is a very important point to note. In all solutions, whether it's acid, bases, salts, or water, the product of H plus and OH must always be this at 25 degrees Celsius. pH, or what is called a power of hydrogen calculations. pH has been associated with a way of indicating the concentration of hydrogen ions in any aqueous solution. It was developed over 100 years ago by Danish scientist Sorensen and is expressed as this in this equation here, that pH is equal to negative log of hydrogen ion concentration. So if you know the hydrogen ion concentration, you all do is to put the negative log of that and you'll get its pH. So let us look at some calculations to make that well understood. Okay, what is the pH of water at 25 degrees Celsius? We know that the hydrogen ion concentration at 25 degrees Celsius is this. It changes, If you raise the temperature of the water, it causes a greater degree of autoionization, and therefore you'll have a greater concentration of hydrogen and OH. This is only for water at 25 degrees Celsius. So this is the concentration. All you do is to find negative log of that. Negative log of this value here is equal to 7. Now when you see these square brackets here, anything in the square parenthesis means you're talking about the concentration, okay? So that's why you see log of that guy there in the square parenthesis means you're talking about their concentration. pH of a monoprotic acid. So if someone asks you to find what is the pH of 0.1 mole per liter HCl, I taught you how to do that already. What you will have to do in all of these, you will have to go and find what is the H plus ion concentration in all of them. Knowing this, okay, knowing that, we just do the negative log of it and you find what the pH of it is. We'll see what we do. We'll ionize our HCl to show the mole ratio of the parent molecule to the hydrogen ion concentration there. So 1 mole per liter gives you 1 mole per liter, right? Now you're going to find the concentration of that. If you remember well from video number 26, where I taught you how to find ion concentration, you can go review that. This is the concentration of the parent molecule here. What did I say? You put it at the corner here, and you multiply by the mole ratio 1 to 1 here. Okay, that's what you multiply by. We'll review video number 26. And this is the concentration of hydrogen ions there. Okay, 0.10. Negative log of that is going to give you 1. All right? Okay. Calculating the pH of a diprotic acid. All right. I did allude to this. We talk about when some acids ionize, they do it sequentially. Sulfuric acid is one of those. So when it ionizes, the first one ionizes completely. So 1 mole of sulfuric acid will give you 1 mole of hydrogen ion. So you're going to get a hydrogen sulfate ion. So before, this was sulfuric acid before. You had two hydrogen ion. This one went off. This one ionized to form this guy here, okay? So this one went off nicely. But look what happens. A negative charge is left on the hydrogen sulfate radical, right? This one wants to ionize, but it does not ionize as freely as this first one here. It is 20% ionized. 1 mole of this will only give you 20% of 1 mole. Okay, let's say that you have that 0.010 mole per liter sulfuric acid, right? How do you go by finding its pH? So do your ionization to show 1 mole of this gives you 1 mole of this. That's nice. So we calculate the concentration of H plus that it produced in the first ionization. So that is the parent molecule there. Write it there. And the mole ratio is 1 mole to 1 mole. And this is the concentration of H plus for the first ionization. If you do a negative log of that, you'll see that by itself will give you a pH of 2. But this is not accurate because we have to do the other part where the hydrogen sulfate is now going to ionize to give you some more H plus. So let's see what happens with this guy now. It is only 20% ionized. So we know this is what the first ionization gave you. Okay, for the first mole. If you find 20% of that, you get this. So you have two sets. You have this set that came out from the first ionization and this set that is coming out from the second ionization. So we have to add that concentration to this concentration, okay, to get the complete thing. So you add that to that. So the final concentration of your hydrogen ion is the sum of those two and is equal to this. And when you do the negative log of that, you can see it's a little bit lower than 2 because we've added some more hydrogen ion. But look, it's a very small difference. There's a difference between, if you did it for the first one alone, it will be 2. And now if you did it for both of them, it's 1.92. So there's a little difference of 0.8. Might suffice to say just use the first one. And that will be representative of the pH of that solution. So I hope you understand that. Let's go that over again. For some acids like sulfuric acid, the first hydrogen comes off freely, so we can find the concentration of that, and we get the concentration to be this, okay? Now the hydrogen sulfate ion is only partially ionized, which is 20% ionized, so we know the first one was that, so 20% of this will be 20 times that. If it said 100% ionized, then we would have put 2 moles to 1 mole, but that doesn't happen, okay, because we said the second hydrogen is reluctant to move off so readily like the first one. And then you do that, you add the two together, and then you find the negative log of that, okay? You want to find the pH of this solution. It's very easy. All you do is to find the final hydrogen ion concentration. I taught you how to do that already. You find number of moles of this guy, then you find its concentration, okay? And then, of course, you know it ionizes, and then you can find the concentration of the H plus there. So you find the number of moles, you know, the mass over molar mass, that's the mass there. The molar mass of this guy is 63.02 grams per mole. That's the number of moles you have. But now you have to find the concentration of that because you're putting that in 200 milliliters of solution. Okay? And C is equal to N over V. This is N. This is your 200 milliliters. In terms of liters, is 0.2 liters. And that's the concentration of your nitric acid. Now you find the concentration of H. Do your ionization equation. And you see it's a 1 mole to 1 mole. Alright? Then what do? Take this one. Put it here. And you multiply by the mole ratio, 1 mole to 1 mole. And that's what it is there. And you get that concentration of hydrogen ion. And then you do a negative log of that. And this is what you get here. All right. Not bad. So when you're given the mass and the volume of the acid, find the number of moles of the acid by taking its mass and dividing it by its molar mass. You'll know the molar mass because you know the formula. When you get a number of moles there, you find its concentration by taking that and divide by the volume of solution that it forms, which is this in this case. Then you do your ionization equation to see the mole ratio. Then you take the concentration of the parent molecule there and you multiply by the mole ratio there, get the concentration of a hydrogen, and you find the pH of that, negative log. Calculating H plus given pH. We're doing a lot of concepts here. You can go back. You don't have to do all of this one time. You can play the video sequentially and extract what part you want to learn, and then you can go back again and see the other part again. If you are given pH, how can we calculate the hydrogen ion concentration? We know that if you're given this guy, we can calculate that guy. Therefore, if you know this one here, you should be able to calculate that. Let's say in a solution, the H plus is this, right? You will find the pH to be 1.0 because negative log of this will give you 1. Okay? So if someone says to you, look, something has a pH of 1.0, obviously, it must have come from hydrogen ion that has that concentration, right? Based on that, they've developed a mathematical relationship to teach you how to find the hydrogen ion concentration, and is equal to 10 to the negative pH moles per liter. So it'd be equal to, I say 1 type sometimes, I would say 1 times 10 to the negative 2 to the negative pH. See, whatever the pH is, make it negative exponent. So if pH is 2, it becomes negative 2. So it's 1 times 10 to the negative mole per liter of hydrogen. So what you have in here is some questions there to find the pH. All you do is to do the ionization equation and do the mole ratio, and you multiply it by the parent molecule. This is the concentration of the parent molecule here. Alright? It becomes a little bit more challenging here to give you mass of the solid dissolved in certain liters. You go about finding number of moles of the compound. Then you find its concentration. Then you do your ionic equation to show the mole ratio, and you multiply by that and you get it like I did before. And then you ask to find the H plus in these. It will equal to 1 times 10 to the negative 2, 1 times 10 to the negative 4, and so on. pH and dilution. If you have a pH meter in an acid, and it shows the reading of 2, and if you pour water into that, gradually you'll find that the pH will rise. So when you dilute an acid, the pH rises. Okay? So look at this question here. I have 10 milliliters of this acid here, right? I diluted it to 100 milliliters. They want you to find a change in pH. First of all, you find the pH of the original solution. Then we find the pH of the final solution and see what the change in pH is. So we have a solution that has that concentration of HNO3, right? So do your ionization. So you get 1 mole for 1 mole. You know the original concentration. This is the original concentration, and that's the mole ratio there. So you get that number of moles per liter of hydrogen, and all you do is to find negative log. So the pH of the original solution is 2. Now we're changing it from 10 milliliters to 100 milliliters. Let us see if there's any change in pH there, okay? Let's see. Find the final concentration. Use this equation. C1V1 equals C2V2. How you can remember that? And we are looking for C2. We know C1 because they give you that 0.0100 moles per liter. You know V1, which is 10 milliliters. You know V2 is 100 milliliters. Change all of those to liters. So you leave C2 as it is there. Leave this and you bring down the V2 there. Taught you how to do that already. So C2 will be equal to C1V1 over V2. This is C1. This is 10 milliliters. And this is V2, which is 100 milliliters. Okay? And this is your new concentration. See? When you dilute it, of course, the concentration gets less. And of course, the concentration of H plus ion should get less. So that will be the final concentration of your hydrogen ion, negative log of that is equal to 3. So original pH was 2. When it diluted to 100, it changes from 2 to 3, right? And there's a change of pH of 1. Okay, it changed from 2 to 3. So note that every time you dilute an acid, its pH rises. The pH scale now, this is the pH scale. The pH scale tells us if a solution is neutral, acidic, or basic. If it is acidic, it also tells you to what degree it is acidic. If it is basic, it tells you to what degree it is basic. So watch this. Anything that has a hydrogen ion concentration of 10 times 10 to the negative 7 is neutral. As the hydrogen ions get more concentrated, okay, know why? Because the negative exponent here is getting less and less. We have a negative exponent that's getting less and less. It means the value is getting more and more. The lower the pH, the higher is the hydrogen ion concentration. Look, if I have a pH of 4, this is the hydrogen ion concentration. If I have a pH of 1, okay, this is the hydrogen ion concentration. So note that the lower the pH, the more acidic something becomes because the concentration of the hydrogen ion increases. The higher the pH, the lower does the concentration of the hydrogen ion get, but the OH ion concentration increases. So while AH plus is decreasing like that, OH is increasing. pH paper changes color depending on the pH of the solution that it is dipped in. If you take pH paper, you put it in acid here, that is a pH of 0, it will turn to that color. If you put it in a pH that has 5, it gives you that color. If you don't know the pH of something, if you don't have a pH meter, and you don't know what is the pH of this solution, put in your pH paper inside there, alright, and see what color it gets. If it turns to that color there, maybe it belongs to the pH somewhere there. I didn't choose the correct color, okay? You can see some common substances, and you can see what pHs they have. Cherry is going to be somewhere, banana here, vinegar here, okay, stomach acid is here, okay, very acidic, okay? And then you can see how some household product also have basic things that what the pHs are, okay? So you look at this table here that shows you how pH changes with dilution of an acid. This is the original pH and hydrogen ion concentration in this table here. And they're showing you when you dilute it, there's a final pH and what is the change in pH and the number of times the solution is less concentrated in H plus than the original one. So let's do the first one as an example, right? Here you're having an acid that has a hydrogen ion concentration of 1 times 10 to the negative 1, which is equal to 0.1, 0 moles per liter, right? This is in scientific notation. Put it like this, okay? Expanded form here, okay? Decimal form here. And the pH is 1. If I dilute this now to make that 1 times 10 to the negative 2, you can see that I'm changing the concentration by 10. And now the new pH is 2. So the change in pH between this guy and this guy is 1. And the number of times that this acid is less concentrated than this acid here is 10 times less. So you can see this value here is 10 times less than that value. Let's do another one. Let us say now you change this concentration of the acid from 1 times 10 to the negative 1 to 1 times 10 to the negative 3. Look, that is it. Put it in decimal form here, get this. What is this compared to that? This compared to that is 100 times less. This pH was 1, now negative log of that gives you 3. The change in pH between 1 and 3 is 2. So every time a solution is diluted to give you a solution that's 100 times less concentrated, there's a change in pH of 2. If it is diluted to give you one that's 10 times less, is a change of 1. Okay? Do another one. Here we have the original concentration here. We are doing 1,000 times less. So this is 1,000 times less than that. pH here is 4 if you do a negative log. Look at the difference between this one and that one, it's 3. So if you have a solution and you dilute to such an extent that the final solution is 1,000 times less than the original solution, there's a change of pH of 3. You can do another one here. We don't necessarily have to start with 1. We start with this one here. See? It's a negative 2. And we go to negative 6. So you can see this one here is 10,000 times less than that one there. pH was 2. pH is 6. Change is 4. Okay? So note that then. This is how pH changes when you dilute something. So when it is 10 times less, there's a change up in pH of 1. If it's 100 times less concentrated, there's a pH change of 2. 1,000 times pH of 3. 10,000 times is a change in 4. So you keep diluting acid, its pH climbs, and you can know by how much it changes depending on how dilute it becomes. So that is how pH changes with dilution. Students sometimes will have some misconception here. You can read that and get some sense. Okay, you make the mistake yourself too. pOH of solutions. pOH now. We have never done that. We have never heard of that before. You'll be doing this in grade 12, but why not introduce it right now? Just like how you have pH, same thing. pOH now is pH was negative log of H plus. pOH is negative log of the OH ion concentration. Okay? Again, they ask you to find the pOH of some things. How do you find the pOH of this solution here? Again, you do ionization to see the mole ratio of the OH to the parent molecule that's produced. Do it again. So here 1 mole of sodium hydroxide produce 1 mole of OH ions. Now you want to find number of moles of this per liter. Take the parent compound there and multiply by a mole ratio here, and you get that concentration of OH there. Do a negative log of that, and you get the pOH to be equal to this, right? pKw and calculations. We know that Kw is equal to 1 times 10 to the negative 14. So if you do a log of this, you will get a value of 14. So pKw is equal to log of Kw, and that is equal to 14. But we also know that Kw is equal to that times that. And again, we can find what OH is. We can find what this is. Okay, we've spoken about that already. Okay, watch now. The question before, we ask you to find the pOH for this. Alright? Before. Now they're asking you to calculate the pH of this very problem here. How do you do that? Alright, you see how you do that. So we found the pOH of that to be 2. Now they want you to find the pH of the solution. Calculate the H plus using the formula. Remember, a solution, I told you, regardless if it's a neutral solution, an acidic solution, or a basic solution, there's some amount of hydrogen ion inside there and OH ions. So if I know one, I can know the other. In this case, I can calculate H because from this, I can calculate the OH. In the previous problem, we found that OH was equal to that. Okay, go back again to the previous problem. See, the previous problem, the very problem there, the OH was found to be that. So the H plus now is equal to Kw divided by what OH is, right? So we take what Kw is, I divide by that, and we get what H plus is. See that? That's the concentration. You see how low H is? OH is this. because the OH is high, which is this is equal to 1 times 10 to the negative 2. That OH concentration is equal to 1 times 10 to the negative 2. And this one is 1 times 10 to the negative 12. Okay, now, we're going to find the pH now. pH is equal to negative log of this. And that is equal to 12. So hold on. In the first problem, that was OH. And when you find negative log, the pOH was what? pOH was 2. The very solution, this one here, we ask you to find the pOH. We did all of those steps. And we get a pOH of 2. Does it ring a bell? That one has a pOH of 2, and this has a pOH of 12. Now watch. When you add up the pH and the pOH of the solution, what does it become? 14. So in every solution now, this is the equation you should know, that whatever the pH is, and you add it to the pOH, is always equal to pKw, which is equal to 14. All right? So if you know pH, you can know what pOH is. If you know pOH, you can know what pH is. So pH will be equal to pKw, which is 14, minus your pOH. pOH will be equal to pKw minus pH. Alright, so if you know these equations, problems become very easy for you to solve. Another one, watch this one. What is the pH of this now? See how they're smart? They're not asking you pOH, because you might say, oh gosh, I have OH. Where am I going to get H from? Remember now, if you find the OH concentration, you can find what's the H concentration. So let's do this one. First of all, you do the ionization equation. You take what you have, multiply by the mole ratio here, and this is the concentration of the OH. pOH, the negative log of that, all right, is equal to this. Well, hold on. We just told you that pH is equal to pKw minus pOH. So you could very quickly find what the pH is by subtracting that value from 14 there. Go back and watch this video again and consolidate your understanding of it. And now problems in grade 12 becomes a piece of cake for you to do. Quickly, all right, you want me to summarize that by words? Okay, this is what is happening, okay? This is what is happening, listen. What we are saying is this. Generally speaking, water at room temperature ionizes to produce these quantities of hydrogen and OH ion. You can see at 25 degrees Celsius, equal concentration is produced. Therefore, water is neutral. Anything that adds to the water that upsets that balance there will either make it acidic or basic, right? So what we're saying here is that at 25 degrees Celsius, because this is a constant value, we can multiply that and we call that value Kw, which is 1 times 10 to the negative 14. So a point to making, regardless if it's pure water, a basic solution, or an acidic solution, the Kw must of water stay constant at 25 degrees Celsius. Anything that increases the H plus decreases that proportionately such that it stays this. Anything that increases this decreases that so that this stays the same. Okay? Alright. Knowing one, you can know the other. If you know OH, you can find H. If you know H, you can find OH by doing that. Okay. When you add acid to water or base to water, some things happen. Initially, water has at 25 degrees an equal concentration of H and OH. And this is the product here. When you add an acid, what is happening there now is this. The acid is holding on to some of the OH there and reacting with them to produce water. In the end, you end up with a higher concentration of H plus than OH. And that's what makes this solution become acid, because the concentration of hydrogen gets higher and the concentration of OH gets lower. But in the end, when you multiply their concentrations, they give you the same 1 times 10 to the negative 14, okay? Same thing is happening in this case here. Before you add the base, water is neutral. When you add the base now, what is it doing? The OH is removing H plus from the water to form water here. In the end, you end up with a greater concentration of OH than H. But when you multiply the two concentrations, it must give you 1 times 10 to the negative. So we said this, in acidic solution, H is greater than OH. Basic solution, OH greater than H. Neutral solution, that is what it is, okay? And then this is what it is. And knowing one, you can know the other there. And the important point to note is this. Okay, in all solutions, regardless of what, the ionic product of this and this must always be this value at 25 degrees Celsius. The pH, very easy, negative log of the hydrogen ion concentration there. You know how to find hydrogen ion concentration, just do the negative log there. Talk about diprotic acid there. How the first one ionizes completely, second one is only partially ionized. So you add the first one to the second one, find the negative log of that, and that gives you its final pH. Alright? And you know how to do this already. I taught you in video 26 how to do that. Find number of moles there, divide by the volume and find the concentration of the acid. Do your mole ratio of the ionization here, and then you can find the concentration of the hydrogen there by multiplying the concentration of parent molecule by the mole ratio there. Alright? Good, I do negative log. Alright, same thing here. It's the reverse of that. Knowing pH, you can find H plus is negative log is 10 to the negative pH. Just put negative value there and you get that. pH and dilution. As you dilute an acid, the concentration of the hydrogen gets less. Therefore, the pH increases. I will show you in that table there. In this table there, we show you how these are pHs of some stuff. To what degree pH changes, depending on the degree of dilution. When you dilute something, when something comes less diluted by 10, right? 10 times less, there's a change of pH 1, 100 times less, pH of pH 2, 1,000 times, change in pH of 3, 10,000 times, change in pH of 4. All right. pOH of solution, just like how you do pH, you can do pOH by finding negative log of the OH ion concentration, and that's it. pK, you find the pKw by finding negative log of the ionic product of water, and that's what you get here. This problem that we're showing you here just now is that in a certain solution, if you have this solution, it has OH ion concentration that can give you, all right, pOH, and it also has H plus ion concentration that can give you pH. And you found that when you found the pOH, right, you found that the pOH in this case was 2. All right. Oh, the same problem before here. This was the same problem here. We found that the pH, the same problem, the pH was 2. Then the pOH was 2. Then you asked to find the pH of that, and what you did was to calculate the H plus there. And when you calculate the H plus, and you find the pH is equal to 12, so we add 2 to 12, you found that is equal to 14. So, doesn't matter what the solution is, when you look at its pH and its pOH value, okay, you add them, it is equal to 14. Okay, and these are some general equations I give you to do. Knowing 2, you can find the other one. All right. So I know it's a tough lesson there today. I hope that was helpful. I did that because you'll be doing the same stuff again in grade 12. So see you again next time.